Hello, I'm Iman Fuad, a third-year PhD student at INRIA. I'm working on detection and measurement of web tracking, and today I'm happy to present you our paper on trackers detection via invisible pixels. Lately, we've all been concerned about the coronavirus pandemic, and I suppose that you've all been, at least once, to the World Health Organization website. But how many of you did actually check the number of third parties inside the website? For those of you who did not, we have more than 10 third parties. Including third-party content became a common practice for website developers. It makes building and maintaining websites easier, but this came with the privacy costs. Third parties can actually track users across websites. Let's see how it works. We present the user's browser in a blue box. Inside the browser we have the cookie database, and in that example we suppose that we have doubleclick.net's cookie in the browser. Let's take this navigation example. Let's say that the user first went to the World Health Organization website that have content from doubleclick.net. We present doubleclick.net server on the right in the red box. In order to fetch the content, a request will be sent to DoubleClick and the browser will automatically attach its cookies. Using this request, DoubleClick will get to know that the user 1234 visited the World Health Organization. Let's say that later on the user went to youtube.com and then to amazon.com that have content from the same third party. So once again we'll have a request to DoubleClick, and using this second request it will get to know that the user who was visiting the World Health Organization before is now visiting amazon.com. Basically, DoubleClick is recreating part of the user's browsing history, or what we refer to as user's profile. The collection of this data will improve the quality of ads. Companies may offer you products you didn't even know you're interested in before, which is very profit-making for advertising companies, but it's very intrusive for the user's privacy. In order to collect this data, companies can perform multiple and complex tracking behaviors. So how tracking is actually done in the wild? During this talk, we'll answer this question using our tracking detection methodology based on invisible pixels or invisible images. When we first started our study, we were looking into the type of content inside websites, and we've noticed that in most of these websites we have invisible pixels. They cannot be seen by the user, but they can still enable tracking. Reason why we decided to look into different request responses leading to these invisible pixels, extract tracking behaviors from these request responses, make a classification of these tracking behaviors, and apply this classification to the full dataset. This figure summarizes the main 5 steps that you follow to detect different tracking behaviors. I will guide you through this figure during the talk. In order to detect trackers, we first needed to simulate user behavior, browse to different websites, and collect the data. For that, we used OpenWPM, an open source crawler. We called Alexa Top 10,000 Domains in February 2019. The call was done in a stateful way, meaning that we only used one browser instance and kept the user's profile, including cookies and browser storage between sites visits. For each domain, we visit the homepage and 10 first links. As a result, we successfully called 8,700 domains with a total of 84,600 pages. As a result of our call, we've collected cookies, HTTP request responses, and the images included in the website. We analyzed these images, extracted those that are invisible pixels, and grouped the request responses leading to these invisible pixels into a subdataset that we refer to as pixels subdataset. As a result of our call, we've collected over 2 million images. By analyzing them, we found that more than 35% of these images are invisible pixels. In summary, 95% of the domains that we've visited contain at least one invisible pixels. To sum up, invisible pixels are a perfect suspect for tracking, but they are also widely present in the web. The third step was to detect identifier cookies. Not all cookies are used for identification purposes. In order to distinguish users, trackers associate them with different cookies. And so an identifier cookie should be unique per user or user-specific. To filter out non-user-specific cookies, we made a second call of the Alexa Top 10,000 Domains from a distant machine. Then we filtered out the cookies with the same host name value across the two calls. The fourth step was to detect identifier sharing. I will not go into details for this step, but you can still refer to the paper to read more about the 6 different methodologies that we performed to detect this sharing. Using this detection of identifier sharing inside the pixel subdataset, we made a classification of different tracking behaviors and then we apply it to the full dataset independently from what kind of content is served. We first split our tracking categories into cross-site tracking and analytics because of their different privacy impact. We've seen before that cross-site tracking enables the recreation of part of the user's browsing history, while analytics enables tracking within the same website, which is less harmful for the user's privacy. In this talk, I will focus on the cross-site tracking. We split it into two main classes: explicit cross-site tracking, where the trackers rely on third-party cookie, and then we have the cookie syncing that relies on the sharing of the identifier. I will start with the explicit cross-site tracking. In each of the class, I'll give one example, and again, for the remaining tracking categories, you can refer to the paper. Today, I'll present to you what we refer to as basic tracking initiated by Tracker that is present on over 82% of the websites that we've visited. So let's see how it works. Coming back to our example, let's say that the user is visiting the World Health Organization that have content from adinaccess.com. Again, a request will be sent to adinaccess to fetch this content. adinaccess sets a third-party cookie on the user's browser, but we've noticed that in this kind of behavior, adinaccess redirects the request to its partner, in this case doubleclick.net, either via HTTP redirection by referring to the doubleclick.net's URL inside the location header, or by including content from doubleclick.net. Using this request, DoubleClick sets a third-party cookie on the user's browser. Using this kind of behaviors, domains can track users on websites where they were not initially included, which makes it even harder for the website developers to maintain all the tracking that is happening in their websites, especially that they can even be not aware of the tracking happening by doubleclick.net in this example. We found this kind of behavior in 82% of the domains. In this figure, we present the top 15 domains performing basic tracking initiated by another tracker. In the x-axis, we have the domain names of the domains that are indirectly included. In the y-axis, we have the percentage of first-party domains. As you can see, google.com is the top domain being indirectly included. It's included in over 60% of the websites. So basically, google.com, by only relying on this kind of behavior, can recreate 60% of the user's profile without even having the content on the website. Now, moving to the second class, cookie syncing, I will present to you what we refer to as third-party cookie forwarding that is present on over 7% of the websites. Coming back to our example, the user is visiting the World Health Organization, and now let's suppose that inside the website we have content from adtrue.com. A request will be sent to adtrue to fetch this content, and we've noticed that in this kind of behavior, the third-party trackers are including analytics services. In this example, adtrue.com is including Google Analytics scripts. I'm marking green the analytics services, in red the third-party trackers. The script will set a cookie on the user's browser with as domain adtrue.com, and so by definition the cookie is a third-party cookie. Then it will send the request to Google Analytics with as part of the parameters the third-party cookie. Using this request, Google Analytics will get to know that the user 123 visited the World Health Organization. Later on, let's say that the user goes to a different website, amazon.fr, that have the same content from adtrue.com with the embedded analytics script. So once again, we'll have the request sent to Google Analytics with the third-party cookie, and this time Google Analytics will get to know that the user 123, who was visiting the World Health Organization before, is now visiting amazon.fr. And so Google Analytics is no longer behaving as an analytics service. Instead, it's cross-site tracking the user, since it's able to link its activity, the user's activity across different websites. In summary, due to this behavior and inclusion of content, analytics services are able to cross-site users. We found this kind of behavior on 7.26% of the domains that we've analyzed. We found 386 unique partners that forward cookies, among which 271 are forwarding cookies to Google Analytics.com. And so Google Analytics by itself is cross-site tracking the user on 4% of the websites. In summary, we detected 6 different tracking categories, and we found at least one type of tracking category on 92% of the domains that we've analyzed. In these figures, we present on the right companies, on the left domains that perform either analytics, that we present in yellow, cross-site tracking in red, or both analytics and cross-site tracking inside the same website in brown. As you can see, domains such as Google Analytics can perform both analytics and cross-site tracking behaviors. Next, we want to understand what kind of content is used to track users. We started our study using invisible images to detect tracking behaviors and make the classification. But then we applied this classification to the full dataset with all kind of content. And so we want to see more generally the content used with tracking requests. In this table, we present the top 5 contents used with these tracking requests. And as you can see, not only invisible images are used, but also HTML files and scripts that could be really useful for the good functioning of the website. Given how intrusive is web tracking for the user's privacy, it was normal to see that in the last decade, the research field on the web tracking exploded. More and more researchers were interested in the detection and measurement of web tracking, but most of these works detected trackers with filter lists. Only until 2018, most measurement studies detected trackers with easiest and easy privacy. In this table, we present papers published in top venues from 2016 to 2018 that relies either on EasyList, easy privacy, or both combined. These filter lists rely on regular expressions, which makes it easy for these filter lists to miss unknown trackers. And given how they became a de facto approach in our community to detect trackers, it was normal to ask how efficient are these filter lists at detecting trackers. To answer this question, we studied 2 filter lists, EasyList and Easy Privacy, that is used with AdBlock Plus, AdBlock and uBlock Origin, and moreover it's widely used in our community, and Disconnect, that is used with Disconnect extension and in tracking protections are integrated with Firefox browser. We compared our tracking detection methodology that we refer to as Behavior Track to Disconnect on the right and Easy Privacy on the left. Let's start with EasyList and Easy Privacy. We mark in blue circle the requests that were detected as tracking requests by EasyList and Easy Privacy, and in pink circle present the requests that were detected as tracking requests by our methodology Behavior Track. So as you can see, over 19% of the tracking requests detected by our methodology were missed by EasyList and Easy Privacy, while over 16% of the tracking requests detected by our methodology Behavior Track were missed by Disconnect. So next, we want to understand why filter lists miss those trackers. The first reason is the usage of first-party cookies in a third-party context. Let's take this example. Let's say that the user visits google.com or just happened to open her browser. So if you're using Chrome browser, then google.com will be your page by default. What happens is that a request will be sent to google.com to fetch the content. Google.com will then set a first-party cookie in your browser, an ID cookie. Using this cookie, Google.com get to know that this user 1234 visited Google.com at this given time. So later on, let's say that the user visits w3schools.com, for example, that have content from Google search engine. So now a request will be sent to Google search engine to fetch this content. Along with the request, the browser will automatically attach the cookie that was set in a first-party context, but is now used as a third-party tracking cookie to Google search engine. Using this cookie, Google search engine will get to know that the user 1234 who was visiting google.com before is now visiting w3schools.com. So basically, google.com search engine is recreating the user's profile, but the filter list cannot block the request to Google search engine in this website, because in this context, Google search engine is providing functional content for the website w3schools.com. We found that 32% of the requests that were missed by EasyList and Easy Privacy and 45% of those missed by Disconnect were using first-party cookies or cookies set in a first-party context. In summary, initially first-party tracking cookies are sent with requests to fetch functional third-party content. So when the cookie was set, it was set in a first-party context, and so the filter list did not block it at this point because it was not tracking request or tracking cookie at this point. Then later on, when the request was using the cookie in a third-party context, it was not possible for the filter list to block requests at this point again, because the cookie was used with functional content, and so the blockage of this request that serves functional content could have led to the breakage of the websites that uses this content. The second reason is the usage of large scope cookies. A domain can choose to set the cookie with the second level TLD, such as google.com, instead of using the full domain, for example, searchengine.google.com. By doing so, the cookie became accessible to all subdomains. We found that 77% of the missed requests by Easiest and Easy Privacy use a second level TLD, while 75% of those missed by Disconnect use a second level TLD cookie. In summary, cookies set with second level TLDs are sent with requests to fetch third-party content from all subdomains, including those that serves functional content. And once again, filter lists cannot block this kind of request because of the functionality that they bring to the website. The last question that we want to answer is how efficient are browser's extensions in blocking all these trackers? We compared the efficiency of browser's extensions to our three main classes, or to our three classes: explicit cross-site tracking that we mark in red, cookie syncing that we mark in blue, and finally analytics that we mark in yellow. In this figure, we present the efficiency of browser's extension in blocking tracking requests. In the x-axis, we have the browser's extensions that we've studied: AdBlock, Disconnect, Privacy Badger, and finally Ghostery. In the y-axis, we have the percentage of tracking third-party requests that were missed by this browser's extension. As you can see, Ghostery is the most efficient among the browser's extensions, but it still failed to block over 26% of the requests that were detected by our methodology behavior track as tracking requests. And so, to conclude, we analyze the invisible pixels that are widely present on the web and are perfect suspects for tracking to define a new classification of our tracking behaviors. We then apply this classification to all kinds of content, to the full dataset, and compared it to browser's extensions and filter lists. We showed that even the most popular consumer protection lists, such as Easy Privacy or Disconnect, and browser's extensions fail to detect these complex behaviors. We also showed that domains serving useful content may track the user as well, which leads to the conclusion that between protecting our privacy or keeping the functionality of websites, we clearly need a more fine-grained approach to detect tracking. For any further details, please don't hesitate to refer to our paper, Missed by Filter List: Detecting Unknown Third-Party Trackers with Invisible Pixels. Thank you for your attention.